mentioned, this is part of the work mainly that has been carried out in the work package 3 of promotion. And there was, in this work package, which was led by Nicolaos Cutululis from DTU, there was quite a lot of work being done on grid forming, initially for diode rectifiers, but I think the work we're presenting now is what we have done relating to black start using wind power plants, and also on the validation process of this new control capability. We have many partners on this project. I'm not going to go into detail because you present them very well, but we have a good representation of both industry and academia. This is the outline. The outline first is a little bit what I wanted to introduce is why we think black start is going to be very important from renewable energy and also from offshore wind, particularly which alternatives we have been studying, which process we have done for validating the new controls, and what are the lessons that we have learned. This is an example of what happened, a blackout last year. It's not the blackout in the UK. This is less known. That is in Tenerife, in the Canary Islands, where we have in red the program generation, and in yellow the actual generation. So there was a full zero, and it took about 9 hours to recover. At the time of the blackout, we had here about 40% renewables, and the restoration was carried out totally using gas turbines. Also, at this point, there was a wind farm that was connected, but was very quickly disconnected not to interfere with the restoration. So if we move to a scenario in Europe where we meet all the renewable energy targets set by the Commission and the different governments, clearly this kind of restoration is not going to be acceptable. It's not going to be acceptable in a country having 60–70% renewable energy, having a blackout, and this energy not being used to speed up the restoration process. Why offshore wind farms are particularly suitable? So in the restoration process, the first thing the restoring unit is got to do is to power up the ancillary services of the traditional units. And you see, this is the case of Denmark, but it's the same in many other countries, that the wind farms are very close connected to traditional units just because the grid is stronger there. So they are particularly suitable for this kind of situation. So what would we like to do? What we like to do is to achieve a green black start from wind power plants. This is a big challenge, but in any case, if we can allow the wind power plants to be able to be plugged in earlier in the restoration process, that's also a big contribution to mitigate the effects of a big blackout. Which alternatives have we been studying for black start? The first one is HVDC connected offshore wind with a cable of about 75 kilometers, 220 kV. And we just studied the sequential black start, which basically consists on having wind turbine with local energy storage powering up by itself when there's enough wind, then powering up the first string cable, then little by little all the rest of the wind turbines in the same string power up. Once we have enough reactive power capability, we power up all the array cables, and then we continue to power up all the different wind turbines. Now we are operating in an island on the offshore wind farm, so we can power up the offshore substation, then the long cable, the onshore substation, the auxiliary loads of non-black startable units, so we can black start them, or even some local loads that we might have in the local island. And when we have the local island operating correctly, obviously what we have to do is to synchronize to adjacent islands. So this is the functionality of this kind of black start. Which are the main issues here? The main issues are obviously, first one, long HVDC cable and transformer energization. This is quite challenging due to inrush currents and due also to resonances. Second issue is what happens if we have changing block loads, which is going to happen in this kind of situation. What are going to be the effects on the electric system, and also more importantly, what are going to be the effects on the mechanics of the wind turbines if all the loads are going to be shared equally between all the wind turbines. And the third issue is fault response and mainly fault recovery. Fault recovery is quite important. Faults are much more likely to happen in this kind of unstable grid situation. And now, since the wind turbines are grid forming, they do not only to be able to do a fault right through, but they are responsible for restoring the system after a fault. So that's something quite challenging when you have that the grid forming is being carried out by a very large number of wind turbines. The second option we have here is to use soft start. This will cover the first challenge regarding inrush currents and resonances between elements. And in this case, what we do is to power up or close all the breakers up to the onshore substation, and then bring up the voltage using a ramp. There are some questions about different ramp rates, but what we found and what is generally found is that over voltages and inrush currents and resonances are much more largely mitigated in this kind of process. Obviously, the issues with block load and the issues with faults are exactly the same once the system is operating. So this is for HVAC connected. The second option for black start, or the second or the third case for black start that we have been studying in the work project, in the work package, is what happens when we have a HVDC connection. So in this case, we have the different wind farms that are going to bring up the system, the offshore VSC station, and then the onshore VSC station. I think Nikos can correct me if I am wrong, but two cases were studied: one with intermediate substations here, and another one without the intermediate substations. So we have been covering a quite wide range of scenarios, of possible scenarios to carry out the blackout and the black start testing of the different controllers for the wind turbines. So what has been the process for validating these controls? So in the three stages that previous presenters have been pointing out about different control validation and interoperability analysis. So the first step we have been carrying out is EMT simulation-based analysis. The second one was real-time control hardware in the loop, and finally real-time power hardware in the loop analysis. So we started with requirements. These functional requirements were slightly different than normal grid code requirements, as we are talking about a different operating mode of the whole wind farm, mainly voltage control and frequency control. Now it's got to be done directly by the wind farm, and those are mainly adapted from NG ESO and ELIA codes for requirements for black start. Then we have studied the three scenarios, the scenarios that we have been talking before, and HVDC and HVDC, and we have been carrying out a lot of test cases on those scenarios just to be able to show that these controllers comply with the requirements. And finally, these simulations have been done also both with the generic controllers and also with controls, black box controls from vendors. The second part that we have been done, or is in part being done also, is validation based on real-time simulation. So we have one part that is being done by the MDGL, including a VTG control hardware in the loop, including a hybrid simulation with aeroelastic codes, power hardware in the loop using a 1 megawatt converter, powering up a section of the cable and a medium voltage transformer. Something that we're doing in Valencia is try to see what happens with the interaction with a lot of wind turbines, grid forming wind turbines with control hardware in the loop, and also including real protection relays to find out also what would be the operation during faults of a large number of wind turbines. And I think we have also some simulations in Aachen, which have been very recently finished on the integration of wind turbines with HVDC links. What are the lessons learned? We have been proposing or putting forward a validation method, which is in line with current validation methods, and we have been using that for both specific and generic, vendor-specific and generic controllers for wind turbines. We have found that one of the objectives we had is to find out if the modifications needed to be done on the wind turbine converters were large or not. And the results suggest that we need relatively small modifications to wind turbine converters. So that's positive, even though the control is going to be very, very different. In some cases, we're going to need a local storage for the wind turbines. Sequential is possible. Sequential black start is possible, but might lead to over voltages and overcurrents due to inrush. We have to be able to study those cases very carefully. And soft start leads always to much faster energization time and minimizes inrush currents and oscillations. These conclusions are valid both for HVAC and for HVDC connected wind farms. Fault recovery is very, very important with a large number of grid forming wind turbines. Also, especially if in some cases you have that the grid forming capability is being provided by some wind farms that are connected to some other wind farms in a close proximity, which are grid following. And finally, we have to be, this control is got to be, black start controls for black start operations got to be very robust. They're going to operate in islanding mode and in a very changing configuration of the grid. So we need to be able to be very robust to changes in grid topology, which can lead to different resonant peaks. We have to be aware that we might have interaction with other converters and generators in the same area. And what is the main conclusion? The main conclusion is that grid forming wind power plants can contribute to speed up system restoration. However, what we need is to have to align the technology development, the technical requirements, because some technical requirements might stop this from happening, and also to provide a business model to be able to pull the technological development.